Okay, so we'll start looking at standard model. Let's just say as model at renormalization. So what we have again, we'll start again. Standard model is made up of three theories, right? But we have this Lagrangian standard model. He called me actually. Okay. So L standard model contains so L kinetic, L Young's, gamma, scale, or the Higgs or whatever. Now, what happens at the one level? Each of them at the classical level are distinct, and we said that each of them have separate class of symmetries associated with them. Right? We looked at scaling symmetry, we have looked at custodial symmetry, we have looked at level symmetries, and all those symmetries. But one group level, this one gets interacting with this thing will get interacted with this thing will get interacted with this, and so on. So each of them completely get mixed up. So at one loop level, you cannot nicely distinguish. This is for our bookkeeping exercise. But the theory itself sees all the sectors of the picture. Each part will see everything else. Okay. Say for example, the typical things which we know, we try to understand everything in terms of QE. Okay. Now, standard model, we have written it this way, but it has three theories. So the first one, the coupling associated to each theory, we write it down. One is alpha, which is the QED coupling. Then alpha W, the B coupling. Then there is alpha as strong. So when you are doing the renormalization, you have to do the renormalization in every coupling. Okay, in every coupling. Now you can ask the question: will alpha will be affected with other alphas? Okay. In not reality. So each one is independent. So each one is renormalized independently. Each one is renormalized. So if you want to write the full Lagrangian, you should also write other terms. This will make it several pages long. Okay. So this is called gauge fixing. This is called ghost terms. Okay. I'll come to each of these things. Now we have to understand everything in terms of the. It is better to understand everything in terms of QED, but this itself is quite complicated. This becomes complicated because this is an abelian gauge theory. This is a non-abelian gauge. These two are non-abelian gauge theories. This is a massive non-abelian gauge theory, so it requires special properties. And this is a massless non-abelian gauge theory. So I'll just talk about some general renormalization properties going from each one. So the alpha is QD coupling. It's renormalizable. How do you know it's a renormalizable theory? It was shown by Feynman, Schminger, and Donovan. That one loop you can normalize QED. And the three basic processes of QED, you can show it that if I renormalize three things, you can, in principle, renormalize it at all. So, three things which you have to do. One is vertex, other is self energy, third one is vacuum. Okay? So this is vertex, self energy, vacuum. The symmetry is conserved, and the symmetry is conserved all operation potential. So this helps, okay, this helps that to show the theory is renormalizable at all operation potential. The scheme to show that QED is renormalizable at all operation potential is quite complicated. It goes under the name BPH. The entire procedure will go this hopefully you learn in TFT2. Okay, very mentioned. Okay, I don't think it will be done in great detail. Okay, but EPHZ procedure shows that you will be renormalizable for all orders. But anyway, luckily, from this we got something called general renormalization theory. Okay, general renormalization theory. From general renormalization theory, what we learned is that if the theory itself doesn't have any negative mass dimension couplings, so the theory is renormalizable. Yeah, as long as the symmetry is conserved and you don't break the symmetry, the symmetry. Okay? And the theory has no negative mass dimension. Couplings with no negative mass dimensions in dimension 4 or any other dimensions. The theory is renormalizable. So after the general renormalization theory has come, you don't have to worry about explicitly showing that using BPHZ procedure that the theory is renormalizable at all orders of perturbation theory. We know that it is. We know that it is. There are these theorems um, which go under the name Weinberg's theorem and so on. So, okay, with which you can show that every graph has a dimension, essentially. Okay. And from that, you can calculate the degree of divergence. And then from the degree of divergence, you can show that the divergences can be absorbed as long as the number of parameters in the theory is equal to the number of divergences you develop. So in QED, how many parameters are there? Let's look at QED. So I just mentioned some results of general renormalization theory. Theory is renormalizable as long as Let me put a word here. Negative mass dimensions. So what this means, there are no, so you restrict your in a dimension 4 theory, but you don't write higher order dimensions. You have dimension 4, all terms in Lagrangian have dimension 4. You don't write higher dimensions. Gauge symmetry is conserved. But all others in perturbation theory. So why do I insist on all orders? Essentially that at tree level you make sure that the gauge symmetry is conserved. At loop level, how do you assure that gauge symmetry is conserved? The technical term is anomalies. Anomalies should be cancelled. There are no anomalies. Another way, okay. And also, how do you show that gauge symmetry is conserved? What identities conserved? This is more restricted to, there are no anomalies in QED anyway. So here this is more related to anyway, parallel anomalies, but there are no such anomalies in QED. Now in QED, if we distinguish, if you write a parallel QED, say if you say only left-handed particles have QED interactions, then there is a problem. But if you have both left and right, then you write the theory is parallel concerned. So as long as this is true, you would assume the theory is renormalizable at all orders. And then you have only three basic structures which you have to worry about: the vertices, self-analysis, and active potential. These are the three things. And if you renormalize them order by order, it will be. That's the basic idea.
So, in a theory with just left-handed electron, so U1 will not be conserved.
If it has a master, the master will break the symmetry.
But it doesn't have mass.
If it does its massless electron, then the theory has chiral QED. Okay? Chiral QED. If it has mass, it also sees the right-handed structure, and then you have parallel left and right.
But massless
Massless QED,
with just left-handed electrons.
I wonder if it has anomalies. Yeah.
So if I have a theory in 5 dimensions, then I can have dimension 5.
You have dimension 5 operators.
So that would be renormalizable. Dimension 5.
As long as it satisfies, but okay, dimension 5, yes, if you write a dimension 5 theory and write it consistently, it should be, you know, as long as you don't say that fifth dimension is, if it is just general 5 dimensional theory, should be renormalizable as long as we don't write six-dimensional operator. Higher dimension. Now, in five dimensions, the Dirac field is two dimensional, not three dimensional. So you have to write only those terms which are valid according to the dimension. Okay? You can write the kinetic term, you can write the mass term, you can write the Higgs interaction.
So one thing I see is that usually when people talk about effective field theory, I think it's in four dimensions, but still they talk about six dimension, eight dimension. So then that is not real.
Those theories are not known. They can be some set of operators which can be removed. But those theories are not. These are all the extra terms are all non-renormalizable operators. And, you can call them irrelevant operators using conventional language. Irrelevant operators. The dimension 4 operators are conventional operators. Less than dimension 4 are super renormalizable operators. So as far as QD is concerned, you can fix the gauge. So do the gauge fixing. Say you can fix any gauge you want. So easiest gauge is Landau gauge or Coulomb gauge or whatever. Okay, and then work with the theory and do the renormalization. And eventually the renormalization scale. Typical renormalization scale choice after doing the one loop integral. If you do it in one loop integral, say for example, it gives you an infinite path. Let's check it out. You take a P, okay, and then so P minus K, okay. So you have an integral over K, which will run from so there's a numerator part. This loop integral will be there. Now this loop integral will have a value. And we can calculate whether it's convergent or divergent. Depending. So this is quadratically divergent. This loop integral. How do you know? It's quadratically divergent. So D for 4 has 4 dimensions. Every P momentum factor contains 1 dimension. So the numerator is 6 dimension. The denominator is 4 dimension. So the superficial degree of this divergence is lambda square. So if you put a cutoff lambda, so this is quadratically lambda square. So this is called the superficial degree of divergence. So this is a quadratically divergent quantity if you use a cutoff. But then we can use something called dimensional regularization, in which this entire integral get transformed into a pole. Okay, by introducing a scale called mu. This is called dimensional regularization scale. This you must have learned in your UNT course. And this introduces the scale mu, and you do the integral in 4 minus epsilon to epsilon dimensions, and the full or the infinity gets reflected as 1 by epsilon. So this entire integral will end up being 1 by epsilon. But then the couplings also will depend upon mu. So whatever couplings which come in the front, say for example, whatever couplings will come here, so this is these couplings will now become alpha. They will be muted. So this is the entire process of this process is called regularization. So there are two steps in renormalization. First step is the regularization to isolate the infinity in the loop interface. Okay. The isolation of the infinity, you can do it either by a cutoff. The cutoff is useful to understand physically what is the scale involved, essentially. Okay. So we'll use the cutoff many times, essentially. But if you want to match it with experiment, cutoff is not very useful. If you want to match it with experiments, you have to use dynamic theory. Because at the end of the day, whatever quantity you are going to compute will be matched with experiments. Okay, you match it with experiments, so you have a renormalization scale which comes in here in the couplings, inside the couplings. Then the renormalization comes. So we'll talk about two schemes. This is a scheme dependent thing because there is now you isolated the infinity, you throw it out. Okay, if you are using dimensional integration, you throw it out, but there are some finite parts, which is gamma, E, ME, and everything, all kinds of this. Now, how many of them you observe into your definition of coupling, and how many of them you throw away? What is the scale of the renormalization you choose? So those are called renormalization scheme. So those are called renormalization scheme, and the two popular schemes are on-shell scheme, called OS. The second one you know, minimal subscript. Now, I am not going into all the details, but I'm just revising the basic pictures. It's like a bird's eye view of entire composition theory, okay? Okay. But just to give you an idea of what is it, what essentially. So, all the renormalized quantities which we match it with experiment are scheme dependent. This is one thing which you should remember. So, whatever you want to match it with experiment, you should ask what is the scheme with which we are matching? Whether it's MS bar, concept. Most of the time we are using MS bar. On-chain was first initially used during LEP, left results. I'll tell you both the things because standard model was first normalized with on-chain scheme. On-chain scheme has its advantages because in this scheme you can define everything properly. Essentially, because you can define it as on the mask of the master or on the master on-chain scheme. So now, depending upon what the theory is, the the degree of superficial divergence is. So, if the degree of superficial divergence is power less than 1 by lambda or something, it's renormalizable theory. Okay, 1 by lambda square, or something like that. Okay, the superficial degree of divergence is lambda, it's log divergent. Okay, If it is lambda by lambda, it's 1. Lambda by lambda. The same power under slope direction. If it is lambda, it's linearly divergent. Lambda squared is quadratically divergent. Typically, within the standard model, you will get up to lambda quadratically. You go to theories with more than two derivatives, okay, like gravity, you'll end up having higher and higher divergence. You'll end up having higher. So, what is the on-shell scheme? On-shell scheme is the way the renormalization scale, because every coupling will now depend upon the scale which is introduced in dimensional realization. Whatever scale is introduced in dimensional realization. And that scale is called the renormalization scale. So, what it makes the entire process of renormalization makes all the coupling constants conservative dependent upon momentum. So, these are called running coupling constants. Heard the word running coupling constants? Running coupling constants means these coupling constants will start running with energy. So, last time I said that if you measure the repulsion of electrons at atomic scale, and if you measure it at very high energy, the electrons are moving very fast, like for example, near a black hole somewhere, the repulsion between the two electrons will be completely different. Because if they are moving with speeds, momentum is very much larger than their mass itself, something like that. What will happen to the coupling? It increases. So, how will you deal with it? You change the renormalization scale, okay? And you can renormalize the charge at two different scales, and you have an equation which relates both. Coupling, given a coupling at one scale, you can derive what is a coupling at another. And that equation is called renormalization. Renormalization group equation. Was first done by Gelman and Lowe. Okay. So given a coupling constant, so typically this is alpha by dq square or dlmq, which is the momentum square, is equal to beta times alpha. Right? So this is called a beta function. So we keep hearing the word beta function left, right, and center. This is nothing but the coefficient in front of the alpha in the renormalization group equation. And how do you get the renormalization group equation? By doing renormalization at two different scales and equating them. So a couple of words about on-shell scheme and MSR. Let's tell you.
So this new renormalization scale, there is nothing to do with the processes which are taking place.
When you want to match it with the next one, say for example. So suppose you want to match it at the next one which is happening at a collider or something at 100 G. So you have to choose a renormalization scale to be close to the exponent for any physical process. Now we are doing a lot of things, say, early universal stuff. So if you are working in early university, for example, okay, you have to worry about what is the temperatures there, what is the scale, energy scale.
Okay. But in the regularization scale, so we are going to a different dimension.
A different dimension, yes. It's a below 4. Yeah, away from. The reason is that uh, the source of the infinity is because we choose all these interactions point interaction. But at some extent, uh, x is equal to 0, okay? Um, so this vertex is defined at x is equal to x0, where there are three fields sitting. It's like the charge is defined at this scale. And as you know that the charge becomes infinity when you sit on the charge. And in the momentum scale, it's like going to q goes to infinity. So that is the source of the infinity. Okay. This happens at the classical level also, right? In some sense that okay, r goes to 0, the potential goes to infinity. It's a point interaction. So there are so it's sitting at one particular space-time point. The interaction vertex is sitting at one particular space-time point. So this is a hard interaction, not a soft interaction. Meaning, if this is dimensionless interaction, okay, that's called a hard interaction. So such hard interaction, because you're sitting there. If it's a dimensional full coupling, there is no such thing because there's always a scale sitting associated with the coupling constant. Okay.
So I'm saying so the
Yeah, did I answer your question? I went on a tangent. Okay, yeah.
so this is a recombination diagram.
Yes.
So you have momentum.
Right.
So that's the particle moving.
Okay. Now, when you come to defining, so this is diagram we typically denoted with P of phi of P, phi mu nu, because you also have mu and mu in this expert corresponding to the polarization. Now, now if you want to define what is the absolute charge of an okay, you have to make sure that after mention that you want to define some intrinsic properties. So if you want to define what is the mass of an or what is the electric charge of an electron, what is the G minus Q of an electron. Okay, these things are defined when the mass of the electron goes to zero, the moment of the electron goes to zero. The external moment, okay, of the electron. Here it's photon, but we should pick other diagrams for it. Okay, so we should pick the other two diagrams. So when the external moment of the electron goes to zero, you define whatever the function comes out to be. That is defined to be one, so that whatever it comes out to be, that is defined to be the charge. So, for example, in this case, we have something called f1 of q square, and f1 of q square goes to zero. You should see. So this is definition of the electric charge. Then there is something called the f2, okay, and then there is a magnetic moment, electric dipole moment. So electric dipole moment is gauge bigger than quantity or not. Magnetic dipole moment is the coefficient of sigma mu. This comes from this direction. It's also defined at q square. The mass is also defined in the same way because you sum over all the diagrams and the mass is defined as E. Essentially, will be actually this ends up being the pole of the propagator. The masses are defined as the pole of the propagator. And so you have to define the scale at which you have to define what are the intensity. And these are chosen to be at q square is equal to zero. Okay. So yeah. Now, what is the on-shell speed? Now, suppose we want to measure. So the loop corrections again essentially. So now okay, on-shell scheme and everything will make a on-shell scheme is the scheme in which you choose the scale of renormalization to be the mass of the particle. All the particles are in their particular mass. Instead of q square is equal to 0, you say q is equal to me. In standard model, it doesn't really. It makes a difference in later on. Standard. Okay. Now all this is fine for QE. What happens for the next theory? Weak interaction. First of all, weak interactions. Any questions on QED? It's just a words of view. For general renormalization theory, just look at Weinberg's volume 1 last chapter. It's a very, I think nobody does renormalization so lucidly as Weinberg. Okay, it's a fantastic chapter. Uh, we should read it. Of course, many people complain about Weinberg because of notation and everything, but still, it is very well. Okay, so now what happens to weak interactions? Now remember weak interactions. Require massive gauge bosons. So if we have directly added, suppose imagine that I don't have Higgs mechanism. I don't have Higgs mechanism. In that case, no Higgs mechanism. Let's assume no Higgs mechanism. You have theory with massive. Why do you need massive gauge boson? I couldn't hear you. Yeah, B and W boson. Why? Short. Okay. Because the interaction span is very short. Okay. So you need extremely short, meaning want the quantum wavelength is around 17 meters, which means that you need particles of water. Okay, that's by MC, and M is roughly 100 G. So you need very extremely short range, right? So you need a massive range.
It is a short because we observe it to be short.
It's observable. Because in a nucleus reaction, just imagine beta. Okay, one neutron just converts into a proton. There is no long distance effect. Okay, there are no long distance effects. You finally suddenly find three particles at the same place. It happens instantaneously at the same place. One neutron is being replaced by a proton and neutron. So it's instantaneous, so almost like point taken. That's the reason the Fermi theory ones, which first got done, had all of them at the same space time. The neutron, proton, electron, antineutron, all of them are the same space.
So it was more or less clear that the Higgs bosons, which are mediating the weak interaction, has to be about 200 G.
Gauge bosons, yes, roughly around the same. This is just conversion of Fermi coupling constant. So what was measured was this coupling constant very well. But this theory is a non-renormalizable theory. So this theory is neutron. Say let's imagine V minus A, proton. So V minus A is let me gamma mu, gamma phi, and then you have gamma nu, gamma mu, gamma phi electron. So people use this to measure all beta decays and estimated what is its value. This value comes out to be one some 10 power minus GeV or minus 2. It's even more accurate in decimal. Okay. Now this can be converted into G squared. So this is an effective theory of standard with a matching given where GF is matched to uh, G squared by NWS. Okay. So you know GF very well just from measuring beta decays. You know all the transitions. There are various transitions, parity, parity, parity preserving, okay, normal beta decays, gamma Taylor transitions, all kinds of things. Sigma, sigma sitting here, everything. They know everything. So all these measurements will give you what is the estimate of GF. The Fermi coupling is very well known. So it's a short range. Now that we have a gauge theory, now you want to write a gauge theory with this. So this requires massive gauge bosons. So the moment you write massive gauge bosons, say you have say all the fermions, there's clash fermions. And so this is just pure kinetic, kinetic plus Young-Mills. Young-Mills also will be the same thing, which is essentially say F mu nu I, mu nu I plus then you can additional term MW square something. This has to be put in by hand because this is what experimental use. Okay, this is what experimental means. Now you don't have Higgs mechanism, nothing. There is no scale, you can't coupling, there is no Higgs. So if you write a weak interaction theory without the Higgs mechanism, this is what it is. Exactly like QD, except with massive non-equivalent gauge theory. With massive. But this breaks two crucial points about renormalization. First, this term breaks gauge. So in general renormalization theory, we see that you cannot break it, right? Any term in the Lagrangian should not break the gauge symmetry. All the terms should be valid at all orders. So this term breaks gauge symmetry. So the theory is not renormalized. There is also one more way of looking at it. So there is some okay, and if you calculate, it also violates something on the. Now, if you calculate WW scattering, the massive gauge boson scattering, it goes through a gamma Z. This is the only diagram. In a theory without Higgs mechanism, this breaks unitarity. Violate. Unitarity is another way of saying that it does not obey quantum mechanics. Unitarity violation is exactly like saying that you are not conserving your property. Okay. So what it actually does is, if you calculate this process, it violates something called the Poisson law. quasar bombs are essentially there just to show that our theory is correct. The WW scattering should be unitary. That means any theories, any scattering in the part of in the standard model should be unitary. So scattering cross section should be unitary means that the probability is not probability of that particular cross section is not going beyond one. Beyond any probability should be unitary. Okay. So this is not unitarized. The word essentially is that this violates the unitary form because there is another contribution which is missing, which comes with the Higgs mechanism. In addition to gamma ray, there will also be a Higgs. If you have Higgs mechanism, and that conserves the unit. So the bad behavior of this and the bad behavior of that with each other, and they give you a good behavior. And you cannot violate symmetry directly. So you're explicitly violating, okay, the gate symmetry. So by general renormalizability, you know that this is a problem. So the equivalent of what identities in non-abelian gauge theories are called Slavnov-Taylor. See what identities in QED. So the corresponding non-abelian identities are called Slavnov identities, and these are good. They have explicit uh, masters. So to conserve this, the only way you can make this work as a renormalizable theory is by introducing these mechanisms. Only spontaneously broken theories, gauge symmetric theories are renormalizable. So that is the conundrum because we want a massive gauge boson by, by experiment. Okay? And whereas the theory says that such theories you cannot make physical connect, right? Essentially. You cannot make a physical connect because those theories are not renormalizable. Okay? Now, how do you solve it? The only way you can solve this is by identification. So, if you want to make physical predictions to a non-abelian gauge theory, okay? This problem doesn't arise in physics. You need to add, you need to add spontaneous discriminant.
Symmetry is valid. So is it guaranteed that the unitary bound also will be valid?
Um, Most likely, yes. Most likely.
But we have something like this in that proposal.
Uh, Photons are the you can have abelian gauge theories. It's there is some mechanism with which you can get away with massive photons, which is called the Stuckelberg mechanism. So with Stuckelberg mechanisms, you can have, for example, dark photons. Many of the models have Stuckelberg mechanism. Okay, rather than directly breaking them spontaneously. Stuckelberg mechanism is completely different mechanism. It allows that particular term. You don't write it explicitly like this, but it's a different, slightly different. Okay. That particular term allows for massive gauge bosons without breaking gauge symmetry. Can be gauging theory. So that's called Stuckelberg mechanism. Who is in fact people say that he is the originator of Feynman diagrams. Okay. 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 But Feynman made it better. But anyway, he's a very smart guy.
So development mechanism can't be used in this case.
It doesn't work in non-binary gauge. For only for abelian gauge theories.
So could it be that these are, I mean, how many gauge bosons we need? I mean, how do we know? I mean, from vitality, for example, do we know that it has to be three gauge
Yeah,
bosons?
we know at least one charge gauge boson from beta T. And then the theory predicts that there should be Newton gauge boson, which is a, and that has been discovered. It allows you for Newton currents. Yeah, that has been discovered. Newton currents have been discovered. And much later, the gauge bosons themselves have been discovered. Okay, yeah, in 74 or something, after the Tooth showed this series renormalizable, people started looking for Newton currents. And they saw Newton currents and which have been covered in this book. Is the famous Guggenheim uh, Gagan or Gagan what I'm saying it right? What is it? Uh, yeah, there is this huge detector in which they discovered Newton current. They discovered positive neutrino scattering of heliums. The first time they discovered neutrino scattering within the standard. And those are the first indication that there is an extra gauge boson, other than the one which is responsible in the
I mean, before that, it was just theory.
process. And then that was established, and the gauge bosons were seen another 10 years later in 1983. 83, UA1, UA2, Carlo Rubio. So, yeah,
If you have some hidden SU2, then that would definitely need its own Higgs mechanism to have massive boson. There's no other way.
yeah. As far as model building is concerned, if you want to, the level of dark matter you're worried about, okay, you don't think so much because you're not worried about reversibility and stuff. You're only worried about tree level. Okay. In fact, people don't even write all the terms around the symmetry. They only write the terms they want and okay. So it is at that level because they're really worried about signatures. They can always say model right now. But you're right. There is a hidden issue. And if it has massive gauge doesn't have massive gauge so one of the popular things which goes around is something called mirror circle, which is used a lot in dark matter modeling. So you have a mirror circle. It's a great standard. There is a Higgs mechanism. And that Higgs and this Higgs can talk to each other. Yeah. Right. Yeah. Any further questions? Yeah. So we need a Higgs mechanism. So the theory is non-reversible without the Higgs mechanism. And we just argued it by two grounds. One, it breaks gauge symmetry, and using general renormalization means it breaks gauge symmetry. And second one is that it violates field. These are the two reasons why the theory is not. So we need to have the Higgs mechanism. Once you have the Higgs mechanism, what happens is only the ground state, the quantum symmetries are completely conserved. The anomalies are preserved, the quantum symmetries are completely conserved. Only the ground state violates symmetry. That means you have these nice relations that MW G square B square. Whatever. MZ square and so on. Yeah. and so on. So you have these because we have spontaneous symmetry breaking. These are no longer free parameters. They are fixed by the web, and the web fixes should be equivalent to your Fermi coupling constant. They are no longer, they cannot take any values they want. They are always proportional to the condensate of these. All the mass flows which violates symmetry are proportional to all the parameters of the theory are proportional to the condensate of. Generally, in our theory, you should have that number of parameters should be equal to the number of divergences you generate. So in theory, you generate the and you have three parameters of the theory: mass, charge, and wave function. Okay, the same way you can do it. So this conserves all the symmetries. The anomalies are shown to be cancelled by the Barty ABJ objective. The same Barty of scaling variance we talked about.
Which one is brilliant?
Pardon?
Zero is brilliant.
Yes.
Then
Oh yeah. Right. Okay. Right. This is fine. No. No. Maybe this is cost per. Yeah. MZ square.
divide by
Yeah. Yeah. No. Once again. G prime by G is equal to tan theta W. So this is what uh, uh, G prime square G prime square by G square is equal to sin square theta W. Yeah, this is cos theta W. 2 theta W. Yeah, this will be what 0.77. And this is fine. This is fine. This is fine. This is also correct. Yeah, you can work it out. So, uh, so where am I? Okay, anomalies are cancelled, and then you can actually make uh, uh, the theory is completely renormalizable. Standard model is standard. We can actually. The main reason is that you don't have free parameters anymore. All the mass levels and everything are fixed by only one parameter, which is your width, which is a classical. All the mass levels, everything is fixed, and you don't have. And the symmetry is conserved. Anomalies are cancelled. Symmetry is conserved at the quantum level, and the Slamov identities are valid at all orders in perturbation theory. Okay, and anomalies are cancelled. ST conditions. Yeah. Yeah. Okay. ABJ means names of people. Okay. Adler, Barbie, Jackie. Who discovered chiral anomalies? they discovered parallel. Now again, here also we had to choose the scheme. So standard model was first renormalized at one loop level. So the theory was shown to be renormable, but actual matching with experiments was not done at one loop. Okay. If you want to match it at one loop, you have to calculate the renormalized quantity. Okay. You can show formally the theory is renormable. Then what? Okay. You have to actually match the parameters. So this is a parameter, this is the constant. It was just first done by Sydlin in the 80s, where he did renormalization of the electric charge and weak charge ZW masses in OS. OS scheme means on-shell scheme. It's a series of papers, started with Sirlin and then Sirlin, Marciano, and everything. They did in preparation for the left, in preparation for the left. So what did they renormalize? Electric charge, weak charge. W and Z was on. These are things which you know. So what it means that if you measure these masses precisely, you can match it with the parameters. And now, in the renormalized theory, as I said, the W mass will contain all these parameters. Z mass will contain all these parameters. It will also contain the Higgs mass. It will also contain the Higgs coupling. It will contain the top quarter. Because I said, at a one loop level, everything gets mixed up. Okay, so you have to fit the entire theory iteratively. Okay, that's what I later on, it was done. Nowadays, you do it completely. You look at lectures of Hollick and the German group, actually. This is the Italian American group. Okay. And this is the German group, which did it in MS Bars. So that this was done in on-shell scheme. So every particle, the renormalization scale is equal to, for the electron is the electron. For every particle, it's on its mass share. Okay, every particle. The top particle sits on its mass. Okay, every particle sits on its mass. So this scheme is called physical. Because every physically when you are measuring, essentially every particle is on its mass share itself. So this is the closest we can come to the experiment. But this is not useful if you are using, we have so many parameters. And if you have running coupling constants, some, I mean, you are measuring running of the coupling constants, okay, in an experiment, if you want to compare two different experiments, okay, if you want to compare some old experiment with this experiment, okay, this becomes complicated. Of course, you can shift from one scheme to another. Ways of scheme, there is a factor which you have multiplied. So you can shift from one scheme to another. But MS became more advantageous, even though it is because in real life particles always sit on their masses. Okay? Particles always sit on their masses. But here there is an advantage because you can connect the theory much easily. Okay, and compare different experiments, run RG equations, so on and so on. Okay, before going to lab results and everything, and what are the implications, the retroequation test, I'll mention QCD. In fact, the MS bar scheme was introduced for QCD first. MS bar scheme was first. So what is QCD? If we look at the QCD Lagrangian, the L kinetic, plus L elements, and that's it. Nothing else. So this has sidebar all the quarks essentially, and a slash psi and quark sidebar psi. This doesn't break the gauge symmetry, and G mu nu A, G mu nu A. Okay, this is your QCD Lagrangian, and this D slash is del slash IGS G mu nu A lambda I. You have to depends on the normalization. Plus L gauge fixing with L gauge. Now there is one important thing which I forgot to mention. How does the symmetry is conserved in spontaneously symmetric broken? In spontaneously broken gauge series, what happens is in the broken part, symmetry gets converted into some other symmetry. It's called BRS symmetry. Okay, so it's called BRS symmetry, BRS transformations. So that's the reason why the symmetry is still conserved in a spontaneously broken gauge symmetry. That's the reason why you can still renormalize spontaneously broken symmetries. BRS symmetries are covered also in Muta, Muta PCD book, and also they are also covered in shorts. I think they are also covered in shorts. Yes. So you do this. This is a massless, unbroken gauge theory, non-abelian gauge. Okay. So this is theory is renormable. Then what is the problem? It's obviously renormable. Essentially, there is nothing which breaks gauge symmetry. There are no high adaptation terms. There are no unitarity issues. Nothing. So the theory is completely renormable from general principles. Then what is the problem? You see, is there any problem? You had someone. Yeah, you said something. Somebody said something. The problem with QCD is in large company. Okay, so it's not sufficient to do calculations at one look. Okay, so large company. Only problem is so that's the reason. So you have to go to two loops, or three loops, and so on, so calculate and match. It's also but anyway, yeah, you can do several loops. You have to do several loops. Even at high energies, it's not small enough. Yeah, obviously you cannot do QCD at all. But in low energy, you have to do either lattice or connectivity, something else. So, at high energy system, alpha is 100 GeV, almost 0.8. 1. So it's already pretty large. So if you are doing experiments at percent level, one loop results will not be sufficient. Okay, you need to do 2 loop, 3 loop. And then there is something called factorization. So we will not deal with it. There is a scale associated with it. You have, in addition to renormalization scale, you also have something called factorization scale, which comes into the picture whenever you are dealing with QCD process. Factorization scale essentially tells you that if you have a strong partner, and if it goes into two other strong partners, you can independently do QCD like this. There are no real cross terms. So you can factorize this entire amplitude into this part plus because you have loops, 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 loops. So you can factorize it. Okay? QCD is always loops, you have to imagine. There are multiple loops. Single process is not. So in this process and this process can be treated independently. There's an answer. Okay? And there are no loops like this. So at certain scale, this process is independent, this process. So if two gluons are going to another gluon, so both the jets can be treated.
This is a fluid
Slightly higher. It's also true at low energy. You have B process. So if you have a B meson going into the chip side, the K shot. Okay. So there I'll complete it. So suppose this B J K shots. Here also so B meson is taking into something like this. So the factorization theorem tells you that you can separate them as chip side and the K shot. There is nothing in between. Extremely physically, extremely important. Very, very.
Why can't we want to
No, no. There is the factorization thing that they can treat them as a independent process. Yeah.
it's because the color is
Color is conserved.
color
Color is conserved independently here and
and it can be like other gate bosons.
no, no. Let's talk only about strong process. You're not worried about weak process. You're really worried about strong process. This is a strong decay, say for example.
And color is conserved independently.
Independently in both cases. So single colorless object goes into two color. It could be two colorless objects in a way. Okay. Yes. It's a very, very, very important thing. The factorization. So it has a scale associated with it. So any processing in LHC will have factorization scale plus the running coupling constant, the renormalization scale. The theorem is it's not a theorem. We know that it works. How can we must be independently measure the zip time to finance without any real, there is no mess in between. Okay? But doing the calculation is a problem. How will you do the calculation? We have so many gluons running around. If there is sufficient energy of the particle, okay, then the gluons will be separated, spatially separated. Now, this is a very naive way of introducing the factorization, but it essentially tells you that I can separate the amplitude this separately and this separately. I can write this as a separate particle and this entire process. So this sum A amplitude will be sum A1 times A2. I can separate the amplitudes. This is very interesting. Uh, one of the people who is called BBNS. Beneke, Neubert, Shakrada, oh, Beneke, Gura, not Gura. Beneke, I forget the second B. Okay, it's called the BBNS factorization. And read the original paper. It's very difficult. Okay, yeah. Okay, but you can try it. This is very crucial. Uh, and it's not about Beneke. Oh, I forget the second guy's name. It's just on my tips, but anyway. Okay, so QCD has only these issues. So if the theory is renormable, you can compute it. Only thing that you have computed at higher orders to make any experimental consideration, because the coupling is large, you have to go beyond one loop. One loop is not sufficient. You have to go to. So with this, uh, we'll come to. We'll come to. So all the three theories of the standard model are independently renormable. I think I have convinced all of you in less than 1 hour or something that all the theories are okay. Okay. So all the three theories of so you do independently in coupling. So before going further, let's give you some examples in which how the crosstalk appears. So independently you can renormalize the theories. Say for example, alpha can be independently renormalized, alpha W can be independently alpha X. Now in a given process, imagine that there is a process which is a weak process. Okay, let's take a simple example. Let's say weak process, crosstalk. So if there is a weak process, say one of the famous examples. So let's say that this process has some magnitude A. Now this process is a weak process. So it will go at some alpha b square times some loop function. Will there be effect of strong interactions? This is a purely weak process. Okay, the B quark is decaying into S quark. Okay, so you can put something, some other meson, so that this becomes a meson. Okay, and it's the new. Will there be process because these are colored particles? Will there be impact of strong interactions? Yeah. So this is a one loop process and weak interaction. Yeah. Somebody was saying something.
In higher order, there may be.
It will be higher order in what? First order in QCD. So let's say that there are QCD corrections. And this amplitude is some number. Let's say this amplitude is 1. Okay? Some factor 1 or something. Now you add QCD corrections. One with QCD corrections. This suddenly jumps 4. Okay. So because QCD coupling is very large, and you're only adding. So this is one loop in alpha, one loop in alpha S. Okay. One loop in alpha is not sufficient when you are dealing with even a weak process. When you are dealing with strong interactions, it's not sufficient. It will have QCD correction. It will have QCD corrections. And one loop QCD is not important. You need four loop QCD to actually match with exponential. And in fact, the theory is lagging behind here. Okay, theory is lagging behind in this process. We have the experiment is calculated up to 1%, and the theory is 5% from experiment. So the QCD corrections. So like I said, there will be a crosstalk between all the things. Okay, neutral is double muted. It's a pure. It's a extreme weak process. Okay, it is two W's going giving you neutrals, two neutrals. Neutrals will not. But then the original particles will still have forms. They will be QCD corrections. Okay, so QCD corrections are omnipresent as long as you are dealing with quarks. Whenever you are dealing with quarks, you should not, whether it's a weak process, strong process. Anyway, strong process, then you have to worry about factorization and stuff like that. Okay, it's a weak process, you have to worry about QCD correction. They will always be omnipresent as long as it is weak. So everything will have QCD corrections, and you can deal with them in a theory very nicely by RG equations. So you can deal with all these QCD corrections properly. Not very difficult actually now. It may have been difficult earlier, but now we have methods to do it very easily. Another place where um, weak corrections will play a role in the QED process is essentially G minus 2. Okay? So the G minus 2, this is just the diagram. So if you take mu1, so you have this. Now this is a W, you can have a W. Okay? The original diagrams are what? This is QED, but then you can have two loop weak corrections to G minus 2, in which the QED is modified by W loops. So you can have bar Z loops. Okay? Two loop diagrams. So these are called bar Z loops, which all are electroweak corrections in a QED process. Electroweak corrections. So G minus 2 also G minus 2. So these are weak corrections. And then there is the electronic vacuum polarization, which contains everything, including pions.
Okay, so experimentally these will be
This HPV, which will contain.
experimentally these will not be as problematic as the key statement.
Uh, the problem is we only have one number here, exponentially. It's a theory which you have to match it with. Whether you're considering all possible theory calculations, contributions correctly or not. Okay. In this case, you know the theory will make a huge jump in the branching ratio. The QCD corrections, even at one loop, make a huge jump. on the trailer, the one with the. Okay, so this is some beginnings I wanted to tell you, and then there are several examples. Okay, so there are several examples which we find in physics beyond standard. Okay, so next week we'll start with the next week. Okay, this week is over. Right, I'm still thinking this Monday. Okay, yeah. So what I do is we will go to something called regularization and then tell what is the result from there. We'll look into that. Then we'll, for the first time, encounter new physics. If there is a new physics, how regularization will put it. Many models are rolled out. If you do it the stop here. Any questions? So today I wanted to finish many things, but I only finished one word. Okay. So, yeah.
You are saying that these two loop diagrams are so they are only already one loop these corrections.
Yeah. Now, sequence is known up to say 10 decimals.
So they
Okay,
are
so you have if something is known up to 10 decimals. Imagine how much the theory should do. Okay, so we want to look at the significance of the relief will fall down. Okay, so to look at that QED is known up to 4 loops, but dominant part 5 loops, partial is known. Okay, I think it's almost done. 5 loops. Later, 50 years or something. 50 to 60 years.
also here you have probably mentioned that QCD corrections you need up to 400.
Yes, that's true.
So the coupling is already 0.1. So
Yeah, yeah.
I look can depend
So what is happening here is branching fraction of BTS gamma BTS gamma is I think earlier it was between 2 to 4 or minus 4 is the branching fraction. Now you want to compute the theory, the error bars are around 20%. So but this is very small. So it's now shrinking this one. This one is shrinking much further. So Messiah he was a visitor here. He computed it within and he's the only one. Nobody can check his calculation. Okay. So there is only one calculation limit. So, so yeah, if these calculations are only done by once in a lifetime by one person, and that's it. We don't know. We have to trust him and we say, okay, there is a difference in the theory.
why can't they compute it?
These are done on computer.
Not, not
No, but the techniques, even have to put it on computer is not easy. Like for example, electric charge is doing only electric charge is done at 2 loop instant mode. Rest of the things are using computers. Okay. Because if you have massive particles in the loops, it's very hard to calculate with external momentum on zero. It's very hard to calculate the loop calculation, do the loop calculation. Like for example, Anand's whole industry is finding mathematical techniques to calculate these loop integrals at loop. But if the master is QCD, it's much easier. But general Feynman diagram, very, very hard. So two loop integrals, standard model is not a renormalized two loop. We don't have two loop matching of standard model. Fully. One loop is done very well. Parts of it are done, many parts of it are not because mainly because there are no enough techniques. So if you build a collider, next generation collider, FCC or all these corrections will come. And we don't, that's the reason why all this industry is trying to
completely.
so just like for LSC, electricity industry, the electric industry will become handle.
So if you have like a electron or muon collider, then you don't have to worry about QCD correction. If you have electron or muon collider, we don't have to worry about QCD correction.
Yeah. Electric corrections will be. Those are much harder. Yeah, those will become important.
This is because the mass of
The mass of the gauge bosons and the loops, all the particles are massive.
So last time you mentioned about kinetic mixing.
Right.
How does kinetic mixing affect?